Welcome everyone. In this video we are going to talk about one of humanity's greatest achievements. That is, of course, you guessed it from the thumbnail of this video, the Schrödinger equation. And specifically we're going to be talking about the time-dependent Schrödinger equation. Now, to start off, let's say we want to consider some state of the system, right? So psi of t, let's say, which describes the state the system is in at time t. And notice I'm using the Dirac notation. If you don't know what Dirac notation is, I would recommend you to look at some textbooks or some videos about it. And also, the proof I'm about to present is from the book written by Sakurai, his quantum mechanics book. So you could also check out what he has to say about the proof of the Schrödinger equation. And obviously he does a better job than I can do because, well, again, I'm directly actually quoting his way of doing it. So I really recommend you look at Sakurai, and also you can learn about the Dirac notation there. That's where I learned about it. Anyways, so let's say that we have the state of the system at time t, and we want to evolve this to some other time. So maybe to psi of t plus dt at time dt later. And I'm saying that we can do this by using a time evolution operator that I will denote by u. So u by definition, and the way I define it, I'll specify, it takes you from time t, right? So it takes you from time t to time t plus dt. And this is an operator, so it's acting on the state of the system. And it acts on the state of the system at time t. And this just outputs the state of the system at t plus dt, right? So this is the operator that we envisioned basically. And now we're going to require some stuff, right? Because obviously the Schrödinger equation is a fundamental equation. It's an elementary equation. You can't really derive it from first principles. You need to, if you want to do a proof from first principles, you need to first set out the principles, right? There must be some axioms you start with. And obviously some people just take the Schrödinger equation as an axiom. For example, when I was learning this in my quantum mechanics lecture, well, the lecture just said, this is the Schrödinger equation. It's a postulate, it's an axiom, and it's fine, but like when you look at its form, you're like, how would anyone just like come up with this axiom? It doesn't really make sense that you could come up with it yourself, right? It's not, like you would sit in your dream and just write down when you wake up. No, there is some thought process behind it. And so in this video, I hope to just like show the thought process behind the Schrödinger equation. So regardless, what am I saying as well? I'm saying this because I'm telling you, we need to have some principles that we just decide to work with. We can't derive everything from first principles. Well, we can do that, but given that we do have some set first principles. I know I talk too much, but I like talking about this stuff, so bear with me. Thank you for bearing with me. Okay. Well, one of the principles we have is, if a state is normalized, we require it to stay normalized under the time evolution. What's that even supposed to mean? Well, what is the norm of the state? If you know the Dirac notation, this inner product will give the state of the state, will give the norm of the state. And if it is normalized, it's going to be 1. So the assumption, the requirement we're making is, if the state of the system at time t is normalized, we want the state at time t plus dt to also be normalized. So that means that we require this. We require this thing to also equal 1. And sorry, the pencil is really not working with me right now. I think it's broken. We'll probably need to change it, but yeah, sorry for that. But yeah, we require this. Well, if we just substitute this line here, let's see what that gives us about the normalization. Well. So I'm just substituting that. So So we have the bra state now. And for the bra state, again, if you know the Dirac notation, so basically, and like, if you don't know the Dirac notation, like, it's really pointless to be watching this video. I really recommend you to check out Sakurai's book, or just drop a comment below. I can do a video about it. But we're going to have the U dagger, right? And like, I've omitted writing the parentheses, just assume it is there. For convenience, I omitted that. So this is the bra vector, right? This is this part. Now we want to write the ket vector, and it's just the usual U, and then the psi of t, right? And we require that this is 1. But we know that, we know that. If this thing here was the identity, we would have psi inner product with psi, which is 1, because psi was normalized to start with. That means we require that in order to normalize states to stay normalized, we require that U dagger times U is the identity operator, which means that U is unitary, which is why, in fact, I was using the letter U to start with. U is unitary. Okay, fine, I mean, all right, that's all right, but like, what's that supposed to mean? Okay, we've established this, we'll get back to this. But like, if we now think about what U means, it's a change, right? It's a time evolution. So if I just want to write about, I can think about it, right? It is an infinitesimal time evolution. It takes a state from time t to t plus dt. But if nothing happens, if dt just goes to 0, if the state stays the way it is, then U should not make any change to the state it's acting on, right? So it's like its first term should be the identity. It should be something that is derived from the identity operator. Because again, if we take the time interval to 0, there is no time for the state to evolve. And that's represented by the identity operator. But obviously, U can't be just I. And in that case, there would be, well, it can't take you forward in time. There needs to be some time-dependent terms as well. And if we're just focusing on an infinitesimal change, which we are doing, this is the infinitesimal time evolution operator, then we can say it will be linear in dt, right? So it will be maybe some a operator times dt. This is again an assumption we're making. But since dt is a really small, since dt is infinitesimal, we could in fact have higher orders and then take the derivative, take the limit in the end, and the higher orders would get killed anyways, but I don't think there's a need to bother with that. We can see, since dt is small, we can neglect all the higher order terms and just look at the linear term. So this is fine, but historically, to get the shape of the Schrödinger equation we have, I will write something funny instead of a, okay? It is something funny, I have to admit. I will write minus I over h bar times h. I here is the square root of 1, square root of minus 1. H bar here is some constant, but while it's h over 2 pi, where pi is the good old pi, not the apple pie, while the pi, that is the ratio of the circumference of a circle to its, what is it called, its diameter. So that's the regular pi. And then what is h? Well, h is the Planck's constant. So h bar, in fact, is the reduced Planck constant. What is h? That's the operator we have. Well, it will turn out to be the Hamiltonian. It won't turn out to be, actually. It's going to be another assumption we make. We will assume that it's the Hamiltonian from the classical mechanics. So that's another first principle, let's say. But we're about to see something interesting something neat about the Hamiltonian now. Using the fact that U is unitary. So if U is unitary, that means, and what is U dagger then? Well, it's going to be I stays the same. Then we need to take the Hermitian conjugate here. So it's going to be I plus I, right? Notice h bar stays the same. It's a real number. H dagger and dt obviously is also a real number. So if you just take their composition now, I'll just write it out. Sound and clear. Just bear with me with this. Okay. Now if you just multiply this, it's going to be I minus I over h bar h dt plus I over h bar h dagger dt. And then there will be a dt squared term, which we're neglecting. I'll say order dt squared. We're neglecting that because we want u to be unitary in first order, right? If you don't neglect it, again, at the end, when you take dt to 0, when you take the limit, because we will have some derivatives, the higher order terms would get killed off anyways. But we want this to be identity, right? This needs to be identity. And again, as I'm saying, we're neglecting the higher order terms. Even though we don't need to, they would go to 0 anyways. Which shows you then that if you just look at these two terms, you can hopefully notice that h needs to equal h dagger, which means h is Hermitian. And in fact, that was not the reason why I used the letter h. For unitary, I used u because it stood for unitary. But here, h, I don't think it stands for Hermitian. It in fact stands for the Hamiltonian. But it just happens that they both have the same first letter, which is quite nice. But we see that h here is Hermitian. Cool? So that's that. Now, like, you might be saying, okay, where is this guy going with it? Well, actually, we're just done. Like, I don't even need to show this properly. I just want to show it because it's cool. But now, we're about to do the proof, actually. We're just basically about to be over with it. If you just look at this line, where is it? If you just look at here, and if you substitute the expression for u, which we argued for, right? And again, what was the argument? It should be something that is derived from the identity, because if dt actually goes to 0, then nothing should change. And we just assume that it's linear in time, and then it turns out that if we write it in this form, the h happens to be something Hermitian, and we associate it with the Hamiltonian from the classical mechanics. And again, that's an assumption. There is no maths that's telling you that h stands for the Hamiltonian. That's just baked into the equation by physicist, by Schrödinger himself. Okay, so I'm just writing u times psi then. Well, what is u? U is I minus I over h bar h dt. And this is going to act, right? This is going to act on the state, right? Psi t, and then that will give you psi at time t plus dt. Now, if we do something, right? So if we just get rid of the parentheses, right? If we multiply it through, you can see, like, we will have the identity times the psi, which will give you the psi. I can toss it to the other side. So I will have minus psi t, but now we don't have the identity anymore, right? Okay, so, and then now if I divide by dt, I know mathematicians don't like that, but I'm totally fine with dividing by dt. We divided by dt now, and then now if we take the limit as dt goes to 0, we will have minus I h bar h psi, and that's going to be on the right. You hopefully recognize that as the derivative of the psi, time derivative of the psi, and this is the psi at time t. Maybe I should be specific about it. And then if we to get the formula people are more used to, maybe if you just multiply by h bar and by I, well, you will have, okay, so we will have the derivative. So if you multiply by h bar, you're going to have the h bar here, and then if you multiply by I, that's going to be a minus 1 on the left, so the minuses cancel, and you'll have an I on the right, and that is, my friends, that is the time-dependent Schrödinger equation, which is satisfied by all the states. Now, there's also the time-independent Schrödinger equation, which is basically an eigenvalue equation, and that is only satisfied by the eigenstates of the energy observable. If that doesn't make any sense to you, don't worry about it. You don't need to worry about it right now. But this is the time-independent Schrödinger equation, and this is the general Schrödinger equation. The time-dependent form can be derived from this by a change of variables, or by just using the fact that well, using the fact that H is Hermitian, so it has a complete set of eigenbases, and that there needs to be an eigenvalue equation, yada, yada, yada. But don't worry about it. Another caution. This thing only works for classical physics. It is not compatible with special relativity. For that, there is the Klein-Gordon equation, which describes particles that don't have spin. And then if you're considering the electron, that's not good enough because electron has a half spin. And for that, there is the Dirac equation, which describes particles relativistically that have a spin of 1/2. And in fact, that's sort of how Dirac basically predicted the existence of not dark matter, of antimatter, right? Of positrons and antineutrinos or whatever, right? I don't know if you talked about antineutrinos specifically, but definitely about positrons. That's basically how we predicted them. But anyways, I really love this topic, so I just keep talking about it. And if you want to hear me talk about this stuff, just let me know in the comment section. I will be more than happy to talk about it more. But anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.